All right, so in this example, we are looking at SATs. Our story here is that we have a random sample of 1,000 high school students, and they gained an average of 22 points in their second attempt at the SAT. Now, we are being told that the change in score, that improvement in score, is normally distributed with a standard deviation of 50 points. Okay, so we have a random sample, right? So that tells us our sample size. We're going to write these things over here, right? We are told that we want to give a 95% confidence interval for the mean score gain. So we know we're working with means. And we also know that they gained an average, that sample gained an average of 22 points. So that we know is the sample mean, 22. And we are told that our standard deviation is 50. Okay, so we know those pieces of information. We know that we are doing a confidence interval for means. And so that asks, so the question is, do we do a Z or a T, depending on where you are, when how far you've read in the book. In this case, sigma is known, right? It is given. Therefore, we are going to use our Z distribution. So that means with our confidence interval of 95%, we know we're going to use Z of 1.96. Okay, so we're doing a confidence interval for mean, and we remember for means, X bar plus or minus Z, sigma over root N, right? X bar is our point estimate, so that is 22, our sample mean. Our Z score, 1.96 times 50 over the square root of 1,000. And this, at this point, is a plug and chug. I do recommend calculating everything that's after the plus minus, the margin of error, separately, and then calculating our confidence interval. So we will go over to GeoGebra, maybe. There we are. Okay. And so we had our Z-score 1.96, and our standard deviation sigma was 50, and our sample size was 1,000. So we've got 1.96 times 50 over root 1,000, and that's going to tell us 3.099. So we've got 22 plus or minus 3.099. And of course, I've rounded that, right? But pretty, we've got a good number of 3.0990, so that works for me. And then we're going to change this, then we're going to do our actual confidence interval, right? 22 minus that margin of error. And if you're using GeoGebra, you'll notice that it assigned this margin of error calculation to be called B. And so I could just say 22 minus B, right? That is the same as 22 minus 3.099, but I don't have any rounding going on there, right? Either way, we're basically getting 18.901 there. And not that we need to do this one, but we will. 22 plus 3.099, 25.099. Okay, so there's our confidence interval, 18.901 to 25.099. So 18.901 less than mu, because that's what we're estimating the population mean, to 25.099. So there is our confidence interval. Now, what does that mean? That's the harder part, I think, right? We can say, remember, you want to have your confidence level, what you're estimating, and what the actual interval is, right? So we can say we are 95% confident that the true or population mean score gain, and if you want to go further, right, of high school students who take the SAT a second time. I'll even do that as SATs of high school students who take the SAT a second time. That's a little long, right? Is between 18.901 and 25.099 points. And so again, yeah, you could have written this a little bit shorter. We are 95% confident that the true mean score gain is between 18.901 and 25.099 points. That would be generally sufficient. All right, I think that's the end of this problem. Yep, so we'll stop there.